To analyze more complicated systems like molecules and crystalline materials, we need to come up with some simple approximate models that allow us to understand what is going on. Some of these models allow quite accurate calculations of such structures and materials, though we're not going to address such methods at the moment. We're going to look, however, at a method that, though not necessarily a very accurate way to look at real problems, gives us quite a lot of insight, an approach called the tight binding method. This method says essentially that when we're looking at one or more usually identical systems, such as, say, atoms in a solid, or possibly in a molecule, we could start out by trying to understand these systems presuming that the electrons in one atom or unit are relatively strongly bound within that unit and only weakly couple over to the next one. While that may not be quite true in the real material or structure, such a model is quite simple to construct in many cases and can give us some quite useful insights. The insights we can get from this model are also relatively broadly useful. A model like this can tell us quite generally what happens as we start to couple two identical systems, for example, by bringing them progressively closer. Here we're going to look at a tight binding model for possibly the simplest problem we might address that way, the problem of two identical but coupled wells. This is, incidentally, a problem we could also solve relatively exactly, at least numerically, without very great difficulty. The reason for using the tight binding model is that it gives us insight into what is going on, insight that turns out to remain useful even as we look at more sophisticated or exact descriptions of such a system. So let's see how we put this model together and what it tells us about the electron states in such a system, a pair of potential wells with a moderately but not entirely impenetrable barrier between them.
So we're formally going to set up a problem of coupled potential wells. So we're going to consider two identical potential wells separated by some finite barrier. So here we have them. Here's one potential well here. Here's another potential well, and here's the barrier in between. And we presume that these barriers on either side go on forever. And solid-state physicists would call the kind of approach we're going to use here something called tight binding, a tight binding calculation. So we imagine these two separate, what we'll call unperturbed potential wells. If we had the left potential well on its own, so just this well but no other one here, and we could have a potential for that, we'd call it V left of Z, well, we would be able to solve this kind of problem. We'd have our first wave function solution here. We could call that psi left of Z. And it would have some energy E1. And we know how to solve that problem. We've solved that one already. Similarly, we could consider just the right potential on its own. So just this potential well here with no potential well on the left. And we would call the potential here V right of Z. And we would similarly be able to solve for this wave function, psi right of Z, which is just the same as the one we solved for psi left of Z, but shifted over to the right. And of course it would have the same eigenenergy E1. Now our actual potential, of course, is this one with the two wells in it, and we're calling this V of Z, this entire potential here. And we could call this a coupled potential well. Note, incidentally, we're going to choose our energy origin at the top here. Of course, we can always choose this energy origin wherever we wish, and it's just going to make our algebra a little simpler here. If we choose the 0 here, so this would be some negative energy, and this would be some negative energy. We can always do that. It's always a choice we can make. So now, because of that, we can say that this potential V of Z is actually simply the sum of V left of Z and V right of Z. So just adding together this potential and this potential gives us this one. So that's just an algebraic convenience. It wouldn't matter what we chose here, but you can see obviously this makes our algebra a little simpler. So with this choice of energy origin, the Hamiltonian for the system simply becomes our usual kinetic energy term, and the sum of these two potentials, V left and V right. So now what we're going to do, really, is we're going to think about solving this problem using a finite basis subset model, if you like. And in this case, what we're going to do is we're going to choose these wave functions in the isolated wells as our basis. So psi left of z and psi right of z. So we're going to choose a basis with just these two functions in it, hoping that that's going to be good enough for our problem, and solve just using these two. Now, these two functions are approximately orthogonal if the barrier is reasonably thick. That is, we're presuming that each wave function is relatively tightly confined within its own well, and with little leakage over into the adjacent well. So we're saying this amount of wave function leakage we see into this barrier here is not very much over here, so we think that probably even in this coupled well problem, there's not really very much leakage of this basis function, as it were, over to the left, and similarly there's not much leakage of this basis function over to the right. Now, this is only an approximation, but we're going to take this approximation in this kind of model. Hence, we're calling this the tight binding model. These individual wave functions we regard as being very localized within their individual wells. Hence, the wave function we're going to use can be written approximately in the form psi is equal to a times psi left plus b times psi right. This has to be the case if we're saying that these are really effectively our basis functions that we're going to use in this problem. We can put this in vector form, of course. We can use it in the same kind of way that we use the finite basis subset approximation with matrices before. So here we have our matrix form. We've got our coefficients a and b, which are just these ones here. And now we're saying, well, we're going to write our Hamiltonian now as a matrix on this basis here. And writing it as an eigenequation, we have this matrix, this operator, operating on the state, is going to be equal to E times the state on this basis. So in this matrix form then, we have, first of all, this matrix element H11. Well, that's just psi left star times the operator times psi left. And because we're presuming the barrier is relatively thick here, the amplitude of psi left is going to be approximately 0 inside the right-hand well. So this is the approximation we make here. So we're saying this basis function is approximately 0 inside this well. So this integrand here, with psi left star here and psi left on the right as well, is approximately 0 inside the right well, because we're presuming that this wave function, psi left of z, is approximately 0 inside the right well. Hence, this term, psi star left of z times v right of z times psi left of z, can be neglected. The potential v right is 0 everywhere except inside the right-hand well. But there we're saying these wave functions are approximately 0. So this integral we're going to neglect. Hence, when we look at this h11 here, we lose the plus v right of z inside here. We're just not going to have that. And of course then this matrix element simply becomes E1. This is just the evaluation of the Hamiltonian for this problem, the left-hand problem, on its own now. And we can argue similarly for h22, which is just associated with the other wave function, with this one here. Hence, both of these are simply equal to approximately E1. For the same reasons that, for example, either psi left of z is 0 in the right well, or that psi right of z is 0 in the left well, then when integrating within either well, we can neglect all of the following integrations, but only, of course, when integrating within either well. So this one will be 0 within either well, because either v right is 0 or psi star left is 0. Within either one of the wells, one or other of these conditions would be true, at least approximately for this one. And similarly, in this case, either V left is 0 or psi right is approximately 0. In one or other well, this will always be the case. One or other of these will be approximately 0. And similarly for these other terms here. So we are, however, going to retain the interaction within this middle barrier here, where the wave functions, although small, are presumed not to be negligible. So we're saying this wave function isn't negligible and this wave function isn't negligible when they're within this barrier. But we are going to neglect contributions from the regions outside this middle barrier, as we've just discussed, because one or other basis wave function is approximately 0 there, at least for these off-diagonal terms in the Hamiltonian that we're looking at now. So we will retain this result. This is the integral within the barrier, and within the barrier we're not presuming this wave function is 0, psi star left, and we're not presuming this one is 0, psi right, and we're not presuming that this Hamiltonian gives us 0 result. Now it is true that the potential is 0 inside the barrier, but this derivative here is not in general going to give us a 0 result. As I said, inside the barrier, v of z is actually equal to 0, so this simplifies to the following integral that we're going to be looking at, and this delta E is going to come up in our matrix elements. Incidentally, here delta E happens to be a negative number. This is not particularly important, but if you're checking through the algebra, you might get confused if you don't realize that particular point. And that's because the second derivative within the barrier here, for example, of psi right, is greater than 0. So this second derivative of psi right is greater than 0 within the barrier, because the gradient is actually increasing in that region. Well, with these simplifications, our Hamiltonian becomes really very simple, and our eigenequation correspondingly also becomes very simple. The diagonal elements we already worked out were basically E1, and all that's left, for example, for H12 here, is this one term, delta E. Remember, H12 involved wave functions 1 and 2 in calculating it, and the only place where at least one of them is not 0 is inside the barrier. Note in practice that this delta E is typically real, because we'll typically work with real wave functions here, although we don't technically have to. But we've left the complex conjugate in here for completeness. Well, we find the eigenvalues of this equation fairly straightforwardly by setting the determinant of this matrix to 0, which is a standard technique. And that is this quadratic equation in this case here has to be equal to 0. And that gives us eigenvalues from the solutions of this quadratic, and they will be eigenvalues E equal to E1 plus or minus the modulus of this quantity delta E. That's the result of solving this equation, or equivalently solving this equation here. And what that means is we're going to get two energy levels here separated by an amount 2 delta E. The magnitude of the separation is that amount. So within these approximations here, the energy levels are split by the coupling between the wells. It's only the interaction within the barrier that comes into this particular calculation here. And these are split in this model symmetrically about the original single well energy. So this single well energy would be exactly in the middle here between these two lines I've drawn. So if we now take these eigenvalues that we've calculated and we substitute them back in here, that is, we choose these eigenvalues, one or other of them, we choose them one by one to figure this out, we then get linear equations that we can solve for A and B. So solving for A and B gives us, after some normalization, here's one of the solutions, psi A I'm calling it, is psi left minus psi right. So I've got something that's positive in the left here and negative in the right. I divided by root 2 here to get this normalized. Of course, the sign of this overall wave function doesn't matter. I could equally have done it the other way up. And always, of course, with eigenfunctions, we could multiply them by any unit complex number, and it wouldn't make any difference. But we'll write this one in this form. And anyway, the key point is that these have got opposite signs. And the other one is this one down here, where these two have the same signs. So psi left plus psi right, and again, the root 2 on the bottom line for normalization. And again, we could multiply this by any unit complex number, and it's still an answer. But the key point is that these signs are the same on both sides in this particular wave function solution. So here are our two eigenfunctions that we get out of this very simple model. The lower energy state here is a symmetric linear combination of the single well functions. It's this one plus this one. The wave function has the same sign in both wells. The upper energy state is associated with an antisymmetric combination. This one and minus this one. So minus this one here. Plus this one, but minus this one. So we have the opposite sign in the two wells for the upper state. So we can also see that we can no longer view these states as corresponding to an electron in the left well or an electron in the right well. In both of these states, the electron is equally in both wells. So that's a difference from our original unperturbed, uncoupled problems. Here the electron was definitely on the left, and here it was definitely on the right. But now in the coupled problem, the electron in both of the states is equally in each well.
This general form of wave functions, one symmetric and one antisymmetric, is characteristic of such a symmetric problem, and it's retained even as we perform more accurate calculations. Bringing two identical systems together leads to a splitting of the degenerate eigenvalues and a coupling of the states. This is a very general phenomenon in quantum mechanics. It occurs, for example, when we bring atoms together to form a crystalline solid, and leads to the formation of energy bands of very closely spaced states, rather than the discrete separated energy levels of the constituent atoms. This calculation has features also found in molecular bonding. If we have one electron to share between two potential wells, as we bring those two potential wells together, two possible states emerge, one of which has lower energy than either of the states the system previously had. If we think of these potential wells as being analogous to atoms, we get lower energy in this lowest state by bringing the atoms closer together. We would have to add energy to the electron if we were to try to pull the potential wells or the atoms apart. Hence, this lowest state corresponds to a kind of chemically bonded state. Now, the actual theory of molecular bonding is much more complex than this because it has to account for multiple electrons in the system and potentials that are not simply square wells, and it also has many aspects to it beyond what we're considering here. However, these symmetric and antisymmetric solutions are sometimes called bonding and antibonding states, respectively. We can certainly see that there can be states of lower energy as a result of bringing these two systems together. These states of lower energy than either of the separate systems possessed, thus energetically favoring this kind of bonding state.